This video is for Chemistry in the Earth System, Unit 2.5, Periodic Trends. Today's essential question is, what is the relationship between the observed chemical reactivity of an element and its position on the periodic table? Our first main idea, reactivity of metals. The alkali metals. The periodic table that we use today was developed after a great deal of experimentation and observation. A fundamental observation was that elements in the same group had similar physical and chemical properties. A good example is found in group 1. The elements in group 1 are known as the alkali metals and include lithium, potassium, rubidium, cesium, and francium. These metals have similar physical properties such as low melting points and low densities. These properties make the alkali metals very soft and easy to cut with a knife. The alkali metals are also highly reactive when placed in water. Not all alkali metals have the same chemical reactivity, however. Sodium reacts more vigorously with water than does lithium. Potassium is even more reactive than sodium. As you go down the group, the alkali metals become more and more reactive when placed in water. Reactivity of metals. The alkaline earth metals. Group 2 is known as the alkaline earth metals. These metals are nearly as reactive as the alkali metals. However, compared to the alkali metals, these elements are harder and have higher melting points. We see a similar pattern of reactivity as we saw with the alkali metals as we go down within group 2. The farther down within the group, the more active or reactive the alkaline earth metal is. Activity of metals. The transition metals. Moving further to the right on the periodic table, we encounter the transition metals, which include the lanthanide and actinide metals at the very bottom. Transition metals tend to be very hard and have high densities. They are also much less reactive than either the alkaline earth metals or alkali metals. This low reactivity makes them suitable for making products that must resist change over long periods of time. Reactivity of metals. Periodic trends. In summary, the reactivity of metals tends to decrease from left to right across the periodic table. The reactivity of metals also tends to increase as you move down within a group. Summary of metal reactivity with water, hydrochloric acid, and air. Over the next 3 slides, please take notes in the form of the data table that you will see. Again, over the next 3 slides, copy down this data table. Metal, potassium, reacts violently with cold water, and hydrogen will ignite. Reaction with dilute hydrochloric acid is very violent, a dangerous reaction that produces hydrogen gas that will ignite. Potassium reactions with air rapidly forms a white oxide and burns violently with lilac flame. Sodium. Sodium's reaction with water reacts violently with cold water. Hydrogen may ignite. Not for sure, but may. Sodium's reaction with dilute HCl. Very violent, dangerous reaction, also producing hydrogen gas that will ignite. Sodium's reaction with air rapidly forms a white oxide, burns violently with a yellow flame. Calcium's reaction with water reacts slowly, producing bubbles of hydrogen gas. Notice there's no ignition here. Calcium's reaction with dilute HCl It reacts vigorously, producing hydrogen gas. And calcium's reaction with air slowly forms, again, slowly as opposed to rapidly, forms a white oxide, and it burns with a red flame. Magnesium's reaction with water reacts slowly, producing bubbles of hydrogen gas. This can burn in steam. Magnesium's reaction with dilute hydrochloric acid. It reacts fairly vigorously, notice the word fairly there, producing hydrogen gas. Then magnesium reaction with air, it burns rapidly with a bright white flame. Aluminum's reaction with water. There is no reaction with water. Aluminum's reaction with dilute HCl. It reacts very slowly. And aluminum's reaction with air, again, no reaction with air. Zinc. Zinc's reaction with water reacts slowly with steam, meaning there has to be a high energy in the form of temperature, high energy water vapor, and it can react, but it will still react slowly. Zinc's reaction with dilute hydrochloric acid reacts fairly vigorously, producing hydrogen gas. Zinc's reaction with air. Zinc wool burns with a bluish-green flame and forms an oxide very slowly in the air. Iron metal's reaction with water reacts slowly with steam, again, the high-energy form of water. Iron's reaction with dilute HCl, it will react, but very slowly. Iron's reaction with air forms a reddish oxide, but iron wool and iron filings can burn quickly as long as there are sparks, again, adding energy. It forms an oxide in the presence of air and water, which we call rust. Lead's reaction with water, there is no reaction. Lead's reaction with dilute HCl, there is no reaction. Lead's reaction with air slowly forms an oxide film and oxides readily upon heating. Again, we're having to add energy to make this work now. Copper metal's reaction with water, there is no reaction. Copper's reaction with dilute hydrochloric acid, there is no reaction. Copper's reaction with air slowly forms an oxide film, oxidizes slowly upon heating. Again, we have to add energy to make this happen, and it still happens slowly. Silver is the last one we'll cover. Its reaction with water, no reaction. Silver's reaction with dilute HCl, no reaction. Silver's reaction with air, no reaction. Our next main idea, reactivity of nonmetals. Again, we're transitioning to the nonmetals here, groups 14 and 15. How do the nonmetals vary in reactivity? Do they follow the same periodic trend as the metals? Again, we can turn to the observations of the elements to find answers to these questions. Carbon is representative of group 14. This element is not highly reactive, although in some forms it can easily form bonds with other elements. Two familiar forms of carbon are graphite, used to make pencils, and then a diamond, which is a crystalline form of carbon. Neither of these carbon forms are very reactive. Nitrogen is in group 15. In its elemental form, nitrogen atoms bond to one another to form diatomic nitrogen, N2. Hence, diatomic, 2 atoms of nitrogen, N2. This gas is found in abundance in Earth's atmosphere and tends to be fairly inert or non-reactive. Reactivity of nonmetals, groups 16 and 17. As we move to the right within the periodic table, we find that reactivity of the nonmetals increases. Whereas carbon in group 14 and nitrogen in group 15 are relatively non-reactive, oxygen in group 16 is more reactive. Moving still further to the right are the halogens in group 17, and these elements are the most reactive nonmetals. Reactivity of nonmetals. Noble gases. The least reactive of all the elements are the noble gases that make up group 18. These elements exist as gases and are colorless, odorless, and inert.
Ever since Thomas Edison invented the light bulb in 1879, we've relied on electricity to see in the dark. In 1910, French scientist Georges Claude sent an electrical current through neon gas to produce the first neon lamp, and the neon sign was born. Neon is element number 10 on the periodic table. The atomic symbol for neon is Ne. An odorless and colorless gas, neon gives off an intense red light under high voltage. Neon is named after the Greek neos, meaning new. It's classified as a noble gas. It sits in the periodic table's second row, period 2. Each atom of neon consists of a cloud of electrons surrounding a compact nucleus that contains almost all the atom's mass. In the most common form of neon, its nucleus has 10 positively charged protons plus 10 uncharged neutrons. Neon has 10 negatively charged electrons to balance its 10 protons. These electrons are found in 2 orbital shells surrounding the nucleus, which can be visualized as being built up from the nearest preceding noble gas, helium. Helium has 2 electrons distributed in 1 orbital shell. Neon has 8 more electrons than helium. The first 2 electrons are found in the sphere-shaped 2s orbital shell. The final 6 electrons fill the 3 lobe-shaped 2p orbitals. The 2s and 2p orbitals are all filled. Neon's second-level valence shell is complete. This makes neon and the other noble gases very stable and extremely unreactive with other elements. Neon is the 4th most abundant element in the universe, but only a very small fraction of neon is found in the Earth's atmosphere. Neon is best known as the source of the reddish glow in neon lights, but it's also been used to make voltage detectors and TV tubes. When an electric current runs through a tube filled with neon gas, the energy supplied is absorbed by some of the electrons in neon's outer shell, and they temporarily jump to a higher energy level. After a brief period of time, the excited electrons fall back to their original location. The energy they lose as they return to their shell is emitted as light, causing neon to glow. The wavelength of the light energy determines the color of the fluorescence. While all those brightly colored signs are commonly known as neon lights, it takes other gases individually and combined to achieve over 150 different colors. Neon produces a familiar reddish glow, while krypton glows a silvery white and xenon green-blue. Artists, known as benders, produce neon signs by bending lead glass tubes into various shapes. Once created, neon signs can last for decades. Today, we see neon all around us in brightly glowing signs in our city streets. The beauty of light has lured us ever since we harnessed the power of electricity, but nothing catches the eye quite like neon.
Reactivity of nonmetals. If we exclude the noble gases, which are the most inert of all the elements, as we've already seen, the reactivity of nonmetals tends to decrease from right to left across the periodic table. The reactivity of nonmetals also tends to increase as you move up within a group. These trends are opposite to those observed for the metals. The element fluorine at the top of group 17 is the most reactive of all of the elements. In summary, we can say that metals and nonmetals both show a periodic trend for reactivity, although these trends are opposing. Metal reactivity increases down within a group and decreases from left to right across a period. Reactivity for nonmetals, other than the noble gases, varies in the opposite way. It increases as you move up within a group and decreases from right to left across a period.
General characteristics of groups in the periodic table. Objective: to learn about some general characteristics of groups in the periodic table. The vertical columns of the modern periodic table are called groups. The elements in the groups exhibit some typical characteristics across the group. The number of occupied principal energy levels, or shells, increases down a group. For example, consider the alkaline earth elements in group 2. The first element in the group, beryllium, has 2 shells. Magnesium, the element immediately below beryllium in group 2, has 3 shells. This pattern continues down the group with 4 shells for calcium and 5 shells for strontium. Elements in the same group have the same number of valence electrons. For example, all the halogens in group 17 have 7 valence electrons. Elements in the same group have similar properties. The halogens typically gain 1 electron to form ions with a -1 charge. In contrast, the alkaline earth elements in group 2 typically lose 2 electrons to form cations with a +2 charge. Elements in the same.
At this point, you should be able to generate a full and appropriate response to today's essential question. What is the relationship between the observed chemical reactivity of an element and its position on the periodic table?